Okay. What do you want to do first?
First two, all besides the very first one. The first two with everything.
What?
Like, flip them in the direction. You have to put the arrow on the other side and make it like this way.
Which one am I flipping?
The second two,
Just the middle two.
This one and this one.
Yeah.
This one and this one.
Those the ones you just said.
No, I didn't say anything. I asked you which ones to flip, and you said the second two, and I don't know what that means.
The middle two. So
There's 4. So
Yeah.
you want to flip those 2?
yeah.
I don't want to do that.
yeah, that's what we do too.
Did you?
So you want the first one to stay the same because the N2H4 liquid right there. Check that one.
I thought I could do one.
That's okay. It was my fault. Don't worry about it.
I'm pretty sure that these are identical.
Well, then why do you want to flip? Why do you want to flip this equation?
That's what I'm wondering. Are they living down the phone?
The first thing.
Oh, they're the same thing.
All right. So, no, I'm not going to do that. Bailey says no. We're going to keep that one the same because we have the hydroxide or the hydrazine both on the reactant side. So we're just going to leave those there. It's in the right state. It's the right number. So that equation is set. The next one. Let's see. Well, this one is good because I get that, and I get this and this. And I get 2 of the 4. So that was a really helpful equation there, that burning of the hydrazine. So now what do we want to flip next? Or do we need to flip anything? What do we want to do? Flip the third one. Because I need this hydrogen peroxide to be a reactant, right? So then I'll do hydrogen and oxygen. Both these as gases. And since I need 2, then I'll go ahead and double times 2. And then all this stuff gets crossed off. And so now I've got my hydrogen peroxide with the correct value. So looks. Oh, crap. That's a typo for me. Because that's a liquid. Because it's not a gas. It doesn't turn into a gas. It decomposes into oxygen and water before that happens. Cool. I love typos. Love them. Alrighty. I do need to get rid of the hydrogens and the oxygens that are on the right-hand side on this one over here. So I will pick a different color. So if I double this one, that turns to a 1, that turns to a 2. And so then I get my hydrogens canceling out. There's 1 oxygen, there's 2 oxygens, and there's 2 oxygens to cancel out. And then there are 2 waters and 2 waters, which gets me up to my 4 waters. So over here, I just need to double that. Oh, I forgot to flop the sign on that one. All right. Anybody, did I make any other mistakes? You okay with that? I think it's 18.3 kilojoules. I think that's what we got. That look good?
What? Yeah.
What'd you get?
Confused myself. I changed the sign when I didn't need to.
Okay.
I just wrote the same equation underneath.
Okay.
I thought I switched to that. Sorry.
So this is exothermic reaction. All right. So calculate the energy needed to heat 250 grams of copper from 22 to 2600, keeping the following specific heat to the melting point, boiling point, blah, 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 blah. Okay. So we only need one specific heat. So we're going to go from 22 degrees all the way up to 2600 degrees. So that total change in temperature is going to be 2578 degrees C. Yeah. Okay. So then I can do a Q equal to 0.092 calories per gram degree C. And my mass is 250 grams. And my temp change is 2578 degrees C. So then I get the degree C to cancel. I get the grams to cancel. The only unit I have left is calories. So 0.092 times 250 times 2578. This is 59,294 calories. What is all of that energy used to do? It's got one purpose. What's the one purpose of that 59,000 calories?
Make the boil.
Nope.
I don't know what we were solving. Bringing the temperature from 22 degrees Celsius to 2600.
Very concrete. Good. Anything else you want to say about that? A little more visual, maybe? All of that energy is being used, like she said, to make the copper temp go up. But when the temp goes up, what's really happening to the molecule, or the atoms in this case? They're moving faster. So some of that energy is being used to make the solid copper move faster in its little space. And then some of it's being used to make the copper, once it's a liquid, roll over the top of each other faster. And some of that's being used to make the copper that's a gas fly around inside the container faster. But all of that energy is being used to make the atoms move faster. So then what we need to do now is calculate the amount of energy needed to melt that copper, one, and two, vaporize that copper, which is why we have the other two pieces. So in the example that we did before, we had five different Qs. We had one for the heating of the ice, one for the heating of the liquid, and one for the heating of the gas, because they had different specific heats in those phases. But I was specific about saying that the specific heat for this is going to be basically the same for all three states. So then instead of having to do three separate calculations, one for the liquid, water, or the solid, liquid, and the gaseous phase, you can just do one shot all the way up. So I still do need to figure out how much energy it's going to take to liquefy this copper. So Q 250 grams, and it's 49 calories per gram. And then to boil it, it's still 250 grams, but this is 12 calories per gram. All right, so the grams cancel, and I get 12 times 250, and I have 49 times 250. So this one is 30300 calories. And this is 12 calories. So, well, I'm missing a zero. There we go. So that plus that plus that, and all of these guys together are going to equal 374,544 calories. And it looks like 2 sig figs and 2 sig figs. So my answer is going to be 370,000 calories. The melting and the speeding up of the atoms barely impacted this total amount of calories, right? Relative to the actual vaporization of the copper, that took so much more energy to do. Okay. Tell me what is happening here. I wouldn't use the word ice, but I would use the word solid. Well, what do you want to say besides that? Solid. I don't know. We can say and since it's a solid, they're speeding up like in place, which you could add. Can you speed up in place? Could you burn off some calories in a very, let's see, what would that be? Like a convoluted or uncomfortable or uncoordinated manner without getting out of your chairs? Sure. No, maybe. Well, I'm saying in your sure exercise machines are a better job of that, but you could like shake your chair around, right? Move around like this, like half jumping jack kind of thing. You're moving faster. You're experiencing more kinetic energy. So that's what's happening to those, but you can't get out of your seat. So that's what's happening to those atoms in molecules or molecules in that spot. All right, so what about here from V to W? What's happening?
The molecules are separating.
Okay. So liquefaction, they're no longer stuck in their spots. You guys have gotten up out of your seats and you're mosh pitting, I suppose. You're all slamming into each other. All right.
So is it still solid?
It is liquefying. So let's zoom in on this.
It's
Solid,
still
solid, 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 solid. Less solid as I move across this. Solid, solid, solid. No more solid. The moment I've hit the portion where it starts to angle back up, now there is zero solid left. But as I'm going through there, just think about like a glass of iced tea or something like that. Summertime, there's still ice in it, and that temp stays what it is until that last bit of ice cube melts, and then all of a sudden the temp starts to go up. So there will be solid until you reach that point right there where the where it goes up. All right, so now what's happening here? I like that. Liquid and the molecules or atoms are speeding up. And then here. Okay. What's my problem with that? Vapor age. It's kind of hard. It's not a normal way to think about it, but tell me about the speed. Let me zoom in again here. Get a yellow or something. Yeah. Tell me about the speed of the atoms right there and the speed of the atoms right here or here or here. They're all the same. How do you know that? The y-axis is the temp, and so they are not heating up. So when when you think about boiling, like I'm watching this pot of water boil, and so the water's heating up. What do you mean by that? The temp's going up, because heating up is sort of nebulous, right? It sort of would mean like you could take that connotation as the temperature's going up, or that it's absorbing heat, because it is absorbing heat, it is absorbing energy, but its temp isn't going up. As it absorbs that energy, what's it using the energy for if it's not increasing its temperature? Breaking bonds, changing state. So it's vaporizing, it's using that energy to vaporize, but its temp isn't changing that whole way across. So like we said, British cooking was horrible because all they did was boil stuff. But at least they knew that while they were boiling, they knew what the temperature of the boiling water was, because it doesn't change as long as there's water there. And then that last part, this last piece up here, right? It is vapor, but
And they can still heat up and mix it up.
so look at the first and the third one.
Yep.
What do I want to say?
The atoms are speeding up.
Oh, one word before that. Vapor or gas. Gas molecules or atoms are speeding up. That good? So they're either using the energy is either being used to speed the molecules up in one of the three phases, or it's being used to change the state of the substance.